Welcome. My name is Terry Soul, and this is Programming Chaos, a channel devoted to fun and interesting programming projects to help you hone your programming skills. Today's project is inverse kinematics. So inverse kinematics is a set of algorithms that are used for controlling both real and virtual limbs. So for example, arms or legs on a robot, or in a creature or a character in a video game or other animation. And there are lots of different techniques for inverse kinematics, but they all have the same basic goal. You have some sort of a target position that you want your limb to reach towards. So it might be something that a hand or a tentacle needs to grab, or it might be a place on the ground that a leg has to reach out to put a foot on. All of these algorithms work in the same general way. You have that target point and you need to adjust the angles in the limb in order to reach that point. The technique that I'm going to be discussing is called cyclic coordinate descent, and it is one of the simpler and faster approaches to inverse kinematics. It doesn't require any matrix mathematics. You don't have to calculate any Jacobians. It's all vector-based, which makes it much easier to understand. It also runs fairly quickly, so it's well suited to real-time applications or putting in things like video games where you need quick response times. The basic idea for this particular technique is that we begin with the joints that are closest to the end of the limb, and we adjust them so that they are facing the target. And then we continue to do that down the limb, sort of back to the shoulder, if you will. And then often you have to repeat that process several times until you've actually reached the target. And in order to understand this clearly, we need to illustrate it. So let me do that. So here I have a sample limb with 3 joints. The end of the limb I've marked with this green star, and then the target is this red star. And so the way that cyclic coordinate descent works is you start with the joint that is closest to the end of the limb, and you calculate the angle of that segment of the limb, and you compare it to the angle from the joint to the target. And what you want to do is rotate that segment of the limb so that it's pointing towards the target, like this. And then the cyclic descent part is we do the same thing at the next joint. So now from this joint, we calculate the vector to the end of the limb, and we calculate the vector from the joint to the target, and we rotate around that joint so that those two are aligned, like so. And then we do the same thing, but moving down to the next joint. So we calculate these 2 vectors and rotate this one so that they're aligned. And you'll notice that we've gotten closer to the target, but we haven't reached it yet. And so the cyclic part, we now go back to our first joint and do the process again. So there's the line to the target. There's the line through the limb segment, and we're going to rotate, in this case, actually the other direction. And now we're getting closer to the target, and now we move down to the next joint, calculate those 2 vectors again, do the rotation, and we get closer and closer, and eventually we should reach the target, assuming it's within reach. That's the idea. The key here, and I'm going to back up one, is we need to calculate these 2 vectors, the vector from the joint that we're interested in to the end of the limb, and the vector from the joint we're interested in to the target, and then we just rotate those vectors so they align. One thing you'll notice is this puts a bit of an emphasis on the joints that are towards the end of the limb. So those tend to make the biggest changes. And I'll put in a trick that reduces that a little bit. One of the things that we'll do is not necessarily do the entire rotation. It turns out that this approach can sometimes be a little bit unstable. And what that means is the limb will flail around a bit wildly in trying to reach the target. That happens particularly often if the target is somewhere back on the limb itself and it's trying to bend back on itself. But you can reduce those instabilities by not making the whole rotation. So instead of doing this entire rotation, you might only rotate 50% of the way. And that takes a little longer to reach the target. You might have to cycle through the whole limb a few more times, which given the speed of computers is not really an issue, but it makes it more stable. The other trick, and I've not seen this talked about in the literature anywhere, although probably other people have come up with it, is to make the rotations of the joints that are closest to the end of the limb smaller. So this joint, my wrist joint, I might only rotate 10% of the way, but my elbow 50% of the way and my shoulder 100% of the way. And what that tends to do is balance out the rotations a little more over the entire limb. And if that doesn't entirely make sense, once we get to the code, it will make a lot more sense. In terms of the code, I'm going to create a class to represent each segment in the limb, and then another class for the whole limb itself, which consists of a series of segments. And the key thing will be knowing where the end of the limb is located and where the target is located, calculating those vectors, and then doing the necessary rotation. The other trick in the code that will look a little odd, we have two loops that in a sense run in opposite directions. So our first loop starts at the joint that is furthest away from the base, that is to say it's closest to the end, and we adjust that joint and then the next joint and then the next joint. So we're working sort of backwards down the arm. But the trick is when I change this joint here, that changes the location of this segment. So once I've rotated this joint, I then have to change the location of this segment. And if there's another segment, then the one after it also gets changed. So I have one loop that says, adjust each of these joints working from the end of the limb backwards. But as soon as I adjust one joint, I have to work my way back out to the tip, correcting those changes. And again, if that doesn't entirely make sense, it will make a lot more sense once we see it in code. So with those ideas, let's start the coding process. I'm going to be doing this in the processing IDE using Java, but the algorithms are pretty simple to apply to pretty much any programming language. I have a little bit of code here, which is basically boilerplate for processing. But what I want to start with is the segment. So each segment of my limb. So let me create a new tab. And for each segment, there's some data that we want associated with it. The angle of the segment, if we want to vary it, the length and the width of the segment, because that gives us nice sort of graphical effects. And then also the XY position of the base of the segment, the joint. So those are all the data members I need. And then I'll create a constructor to set those values. So there's my constructor. The next thing I'll want is just a way to draw each of the segments, so a display function. And this is fairly straightforward. The approach I'm taking is to push the current coordinate system, which is represented as a matrix, onto a stack so we can remember it for later, translate to the base of the segment, rotate in the direction of the segment, and then we just draw a line whose width is the width of the segment and whose length is the length of the segment. So basically move the coordinate system to here, rotate so that this is the X direction, and then I can just draw the line in that direction. So that's pretty straightforward. The more complicated function is the update that has to update the angle of the limb segment. So let's put that in. And for the update to work, what we said we need to know is what is the location of the target, and also what is the location of the end of the limb so that we can calculate those two vectors and rotate one to the other. So I'm going to put those in as arguments. There we go. So this is the X position of the end of the arm. This is the Y position. This is the X position of the target and the Y position of the target. Another approach would be to pass in, for example, actual vectors instead and rotate the vectors, but I'm going to do it just using the XY coordinates because I think that makes it a little easier to translate into other languages if you don't have a good vector library handy. But I still need to know what those angles are, so I'm going to calculate the angle to the end of the limb and the angle to the target, and then I can do the necessary rotation. There we go. So I'm using the arctan2 function, which if you give it the difference in the Y positions and the difference in the X positions, tells you the angle between those 2 points. And I'm using the X and Y, which is the base of the joint. So for example, the base of the joint, and then I'm using the end of the arm. So it's going to calculate the angle from this point to the end of the arm along that vector, which is what we need. And then I need to do the same thing from the joint to some target. I don't have a target in this image, but to some target. And it's basically the same calculation. Except that now the goal is the target position. And then I just need the difference between those. And then I rotate my angle by that difference to line them up. So there we go. That's all I need for the update function. And so now that I have a segment that I can update and draw, what I need to do is create entire limbs. So let's go ahead and do that. So the limb should know what its XY location is, sort of for the base of the limb. And then it needs to keep track of where the end of the limb is. And it has to have an array list of all of the segments. So, right, all of the segments within the limb, which I'll put, as I said, into an array list. And if I want to be able to vary the number of segments easily, I'll put in a data member for that as well. And then we need our constructor to construct our limb. So I'll create the array list. Let's go ahead and spell segments correctly. I'll set the XY location, and I'll just set it at the middle of my window. I'll start with 4 segments, and now I can go ahead and add them all to the limb. So I'm just going to add a series of new segments to my limb. I just need to make sure that I pass in the right arguments for my constructor here. So I need to pass in an angle, a length, a width, and then the XY location. So the angle, I'm just going to start with all of those as 0, and they'll be corrected by the algorithm itself. For the length, I'm going to set it up so that my segments have slightly different lengths, and I'm going to use the map function to do that. So the idea is I'm going to map the variable I, which is the number of the segment, and it ranges from 0 to the number of segments. So I want to map a value between 0 and what turns out to be 4 to the length of the limb that I want. And I'll start with a fairly short segment length of 50, and then I'll extend them as I go out. So each section of the limb will get longer as I go. You can change that however you want. I just think it sort of gives a nice effect. So that takes care of the length of the segments, and then the next thing I need to do is put in the width of the segments. So I'll do the same kind of math. But in this case, I want to start with a fairly thick segment and then have it get narrower, so less wide as I go towards the end. And then I need to put in the XY position, and I'll actually just put them in as the XY position of the limb itself. Again, this seems a little weird because it means that each segment will really start right there, but we'll very quickly adjust them so they're all following each other the way they should. So that takes care of all of the arguments to create the segments for my limb. And let's see here. I'm missing a parenthesis, one to close the new segment and one to close the add. So that is my constructor. It constructs, in this case, 4 new segments, and they each get their own length and their own width, and the angle and position doesn't matter too much because that's exactly what the algorithm updates for us. And so to get that update to happen, we need to write the update function. So let me do that. So the first thing I need to know is what is the last segment, because I'm going to use that as a bound on my loops. So I'll just take the size of the array list -1. I could also probably just use the number of segments because those are equivalent. This works a little better if for some reason down the road you're like removing or adding segments to a limb. This is guaranteed to be correct. And then I'm also going to need to know which is the last segment. And those will both be useful in a minute. So now I need to do the process of starting at the end of the limb and adjusting each angle, working back towards the base of the limb. So there I'm using my end to start at the end of the limb. So the next thing I want to do is calculate the location of the end of the limb so that I can pass it into the segment update function, right? To update a segment, it has to know where the end of the limb is. So the end of the limb, this end X position, is the X location of the last segment, but then I have to calculate where the end of the limb is relative to the start of the segment. So it's the last dot X plus the last dot length times the cosine of the angle of that last segment. And similarly, the Y location is the Y location of the last segment's joint plus the Y value, which is calculated using the sine. So that gives me this XY position. And then I can get the segment that I actually want to update. So this is the segment I need to update. And so I tell it where the end of the limb is located, which I just calculated is end X and end Y. And then I also need to give it the target. And in this case, I'll just give it as the target, the location of the mouse. So my limbs are going to try and follow the mouse around. And that will update this angle so that as required by the cyclic coordinate descent algorithm, it's pointing in the right direction. The issue that I talked about earlier is, let's say I'm updating this angle here, so I'm rotating this limb. Well, that means that I now have to update the XY position of all of the limbs that come after it. So this is my loop that sort of goes from the current joint to the end, updating all of those positions. So U is the segment that I want to update. And in order to update it, I need to know the location of the segment right before it. So I'm going to grab that one as well. And then the new position of the segment that I'm trying to update is the position of the segment before it. So the J-1 segment, plus the length of that segment times the cosine of the angle of that segment. And similarly, U dot Y is the Y location of that segment plus the length of the segment times the sine of the angle of that segment. So this updates all of those locations using that sort of double loop that I talked about. It starts by updating this segment and then works backwards. But every time it updates a segment's angle, it has to update the location of all of the other segments. And let's see, I've got some errors here that I need to sort out. End X, let me scroll up. Yes, I used capital up here for the end of the limb, capital X and Y. So let me correct those. And misspelled segment. There we go. Okay. So this does all of my updates for me. And then the last thing I need to do is display the limb. So let's go in and put in a display function. And that's actually quite simple. For each segment in my list of segments, just ask that segment to display itself. So now I just need to go to my main code and actually create a limb. And I'll call it L1. Let's make that a new limb. And then in the draw loop, all I need to do is update it and display it. And assuming there are no typos or any other errors, this should work fine. Let's see, there we go. Out of bounds exception. So what did I do wrong? You probably spotted this error while I was typing it. If I want to go from n back to 0, this has to be a minus minus. So the problem was I started at the end and then tried to increment instead of decrement. And while I'm at it, let's correct two other minor issues. So again, one you probably noticed, this should be the height times 0.5. And in my main draw loop, I probably want to fill in the background each time. So that erases the screen, so we only see one version of the limb. And there we go. You can see that it is following nicely the mouse pointer. If I go out too far, it just reaches out to get to the mouse, and otherwise it tries to follow it pretty well. There are, as I mentioned, some instabilities. So if I try to come all the way back in, it flails around a bit before trying to figure out how to reach that point. And you'll also notice right there, for example, it takes a lot longer for the joints near the base to adjust. So if I twist this all up and then reach out, that's those joints near the base of the limb taking a little longer to stretch. And so we can fix both of those problems a bit by changing how we handle the adjustment in the segment update. So let me show you what I mean by that. So right here where we're doing our update, I am simply rotating that angle to align properly. And that gives the fastest update, but it also can lead to instabilities and puts that emphasis on sort of the end joint. So what I'm going to do instead is put in sort of an adjustment factor here, which is smaller than 1. So instead of rotating all the way, it'll just rotate part of the way. And I'm going to set it up so that the limbs near the end have a smaller adjustment, and that helps balance out the movements with less emphasis on the end. Now, of course, that's not going to work because I haven't defined the adjustment. So let me add that to my data members. And then I also want to pass that in as yet another parameter. I already used A, so let's use AD. There we go. So now the variable exists, and the reason that I made it part of the constructor is so that at the limb level, where I'm now getting an error, I can pass in a different adjustment depending on which segment of the limb I'm worried about. So let's go in here and add another parameter. And once again, I'm going to use my map function. So I'm mapping from which limb number I'm on, which ranges from 0 to the number of segments. And for the 0th limb, I want the largest adjustment. So I'll let that one do a full adjustment. So that's, you can think of it like the shoulder, and that's going to fully rotate. And then as I go out towards, in a sense, the wrist, I want those rotations to be smaller. So maybe make that, whoops, comma 0.05. So now the shoulder will do the biggest rotations in terms of the adjustments, but on the other hand, the algorithm usually has that be the smallest adjustments, and those sort of balance out. The one other issue I have to address is whenever you're doing a partial delta like this, you have to make sure that it's in the range minus pi to pi, or you get other odd instabilities. And so there's a way to do that using a modulus operator. I kind of like to just use it, do a loop, because logically it makes more sense to me. So the idea is that if my delta is less than negative pi, I'm simply going to add 2 pi to it. And then the same thing, if delta is larger than pi, I'm going to subtract 2 pi from it. And that makes sure that my delta is always in the right range. And we have to do that because, of course, you can loop around multiple times and get values that are much too big. And then when you do adjust by just a percentage, it doesn't actually necessarily adjust in the right direction. So the difference here is subtle. But the idea is we get more rotation sort of at the shoulder and elbow joints, if you will, than we do at the wrist joint. So it all kind of balances out nicely. So there we go. We'll still have some instabilities, but they're actually, hard it is to imagine, a little less than they would be without that adjustment factor. It's worth noting that we only run into those problems when an arm bends all the way back on itself, which quite often won't happen, right? If this is just meant to be, say, a walking limb, it walks fine. As long as it can only reach out and back so far, we don't have any problems. Another adjustment that is often made is you can put limits on how far a limb can bend. So, right, my elbow can only bend so far. We don't have any of those limitations here, and that can lead to these instabilities. If you add in some limitations, that kind of fixes it. So that's the basics. It's worth pointing out that the way that this code is set up, we can fairly easily change the limb. So I made this one to be shorter segments towards, if you will, the shoulder or the hip, if that's a leg, and then the segments get longer. You could invert that. You can also easily add more segments, right? So if I go to my limb, I can simply say, well, instead of 4 segments, I want, say, 8. What I should do then is also make them shorter. So instead of varying between 50 and 150, I don't know, maybe I want to go between 30 and 100. So more shorter segments. And it twists around fairly nicely. And again, you can see it takes a little while to stretch out. And then if you want something that looks less like a limb and more, for example, like a tentacle, we could add a lot more segments. So let's go out to, say, 30 segments and make them all quite a bit shorter. And I'll make them all the same length. So let's just do a length of 10 each. So there, now we've got something that looks like a tentacle rather than a limb, and it's just because it has a whole bunch of segments. And from here, you can do things like change the color, you can add little circles around each one to highlight the joint, you can add a hand at the end, but there's our nice simple inverse kinematics. If you want to do something like walking, then you just say, well, I want repeated locations so that it walks back and forth. There we get a little bit of instability twisting because I moved it too quickly. It should straighten itself out here in a moment. So lots of things that you can do from here. Other cool effects are to color each of the segments slightly differently so that you get a nice colored limb. You could replace the lines that I've drawn with, for example, little images with textures, maybe with suckers if you want it to really look like a tentacle, and so on and so forth. But as you can see, the algorithm itself to do my inverse kinematic so that it's reaching out for the target, not actually all that complicated. So thank you for your time. If you get any really cool results, please feel free to put in a comment, and happy coding. Welcome back. After reviewing the video, I realized there's a couple of concepts that it might be helpful to go into a bit more detail on. So here we are. The first thing to realize is that the way the code is set up on every draw loop, that is to say 60 times a second, we call the update function once, which means all of the segments update once, which might not be enough to reach the target. And there's two things we can do. We can either slow that process down even more so that you can watch the limb sort of reaching out, or we can speed it up so that it follows the target much more rapidly. So I want to slow it down first just so that we can see what's going on. And it may be a nice animation effect depending on what you're looking for. To illustrate this, I'm going to go in and adjust my limb to having only 8 segments, and I'll make each one fairly long to make it a little easier to see what's going on. And because I want to slow down the movement, I'm just going to go into here where we adjust the angle and multiply that by a fairly small number. 0.03 works pretty well. And now you can see when I move the mouse pointer, it takes a while for the arm to reach that target point. So you can see how it's moving, and it takes a while just because all of the adjustments are much smaller. Maybe the kind of animation that you're looking for where you can see the arm moving. Or we can do the opposite. When we go to do an update, we continue to update without redrawing the screen until the arm has reached the target. So let's do that, which is kind of the opposite of this going slowly. So I'll remove the 0.03, and we're going to go into the limb where it does the updates. And so the first thing I need to know is whether the limb has reached the target yet. So I'm going to add in a new variable, which is going to be the distance between the target, the mouse XY, and the end of the limb. And to do that, I need to recalculate the end. So let's copy this over here. So I'm going to calculate the end position, and then the distance is going to be the typical sort of square root of the squares to calculate that, the distance from the limb end to the target. So there's the square of the distance plus the square of the y distance. And so that tells me how far the end of the limb is to the mouse pointer, which is my target. And then I'm going to keep looping until that distance is small enough. So for example, while d is larger than 5, and I'm measuring things in pixels, so 5 pixels is quite close. I just want to keep doing that loop. Now there's a problem with this, which is if the target is out of reach, the distance will never be less than 5. And so the other condition is I only want to loop so many times. So I'll put in a counter. And then I'll say, while the distance is greater than 5 and the count is less than 100. The other thing I need to remember to do is update both of those. So I'm going to increment the count and I'm going to recalculate the distance. And so now it will do a maximum of 100 updates to try and reach the target, but it will stop earlier if the distance gets to be less than 5. And so here you don't see really any motion. It just instantaneously follows the mouse pointer, because as soon as I move the mouse, it does a whole bunch of cycles in order to reach the target position. So there's 2 nice variations depending on what effect you want. You can either slow things down and sort of watch the limb move, or you can speed things up and it pretty much perfectly follows the target. Excellent. Thank you very much for sticking around for this little piece. Happy coding!